Next, we'll consider what we call permutations and combinations as we continue to look at counting rules. So let me introduce this with this example. So it says, consider 3 students, Beth, Ed, and Rich, who are competing for 2 scholarships. One is a $1,000 scholarship, and the other one is a $500 scholarship. No student can be awarded both scholarships. We're going to make a list of the possible ways that the scholarships could be awarded. In other words, we're going to list all the possible arrangements of these 3 students, but we take 2 of them at a time because we'll be picking just 2 of them to award these scholarships. So let me make a list here, and I'm going to start with Beth. So the people awarding scholarships could give Beth the $1,000 scholarship, and then Ed could get the $500. So you can kind of think of this as like first place, second place scholarships. And then we could still stay with Beth getting the 1,000, and Rich could get the 500. And then let's go with Ed first. So Ed, first place, getting 1,000, and Beth getting the $500. And then we could have Ed get the $1,000 and Rich get the 500. Finally, Rich could be first place winner and get $1,000 with Beth getting 500, or Rich could be first place and second place could be Ed getting the 500. All right. So we've got all the possible ways that we could give out scholarships. So if we just count here, 1, 2, 3, 4, 5, 6. So it looks like there's 6 different ways. And I'm actually just going to number these. So these are all the choices. If there was a scholarship committee handing out these scholarships, they would choose one of these 6 possibilities to award the scholarships. So for a moment here, I'm going to focus on this one, Beth, Ed. Beth gets 1,000, Ed gets 500, as opposed to Ed, first place, 1,000, and Beth 500. So when we talk about arranging objects and we say that order matters, so order matters means that the outcome, Beth first place, Ed second place, is different than if we would change the order. So outcome Beth Ed is different than outcome Ed Beth. Right, Ed getting first place and Beth getting second place are 2 very different things, right? So the position that we put the people in, first place, second place, is resulting in something new. So it certainly matters to them, right? In this outcome, Beth gets $1,000. In this outcome, Beth only gets $500. So different arrangements are resulting in different outcomes. So that's what we mean when we say order matters. So when I count out all the different ways to arrange these people where the order does matter, switching orders makes a difference, we call these arrangements permutations. So a permutation is an arrangement of objects where the positioning of those objects does matter. So it does make a difference. So in this case, let me fill in the blank here. So there are 6. These arrangements are called permutations. And easy to remember it as P permutation is like positioning. So order matters or positioning matters. So there's 6 permutations of these 3 students taken 2 at a time. Okay, so let me compare this with our next example. So consider these same students, but this time we're going to choose 2 of them to be on a doubles team to represent the school at a tennis tournament. So from these 3 students, Beth, Ed, and Rich, let's list all the possible ways to choose 2 students to be on the doubles team together. So let's do the same sequence here. Let me start with, I could pick Beth as a player and make her doubles partner Ed. Or I could pick Beth as a player and make Rich her doubles partner. So that's one team, that's another team. And then we could pick Ed to be a player and make his partner Beth. But this is where we stop for a moment, because if they're playing together on a team, Beth, Ed is a team, That's the same team as Ed Beth. So in this situation, it's basically two equal people, two players together. So we're not saying this person is captain and this one's co-captain. There's no sort of first place, second place. There's no sort of ranking or positioning. It's just two people on a team. So in this case, we say order doesn't matter. So the way I wrote those, we weren't positioning them. We were just putting two people together. Sometimes you can think of it like a collection of people on a team. So when you're on a team together, order doesn't matter. There's no ranking, no positioning. So in this case, the outcome, Beth Ed, is the same outcome. So it's the same outcome as Ed Beth. So those are the same team. I'm just going to cross it out. That does not count as a new doubles team. All right, so then we can continue. So there's Ed Beth. We're done with that one. So then we had Ed Rich. And I don't think we have them together yet on a team. So that would be a new team. There's my third team. And then Rich Beth was next. Rich Beth. I think we already have that team right there. Beth Rich, there's the team. That's the same team. And then Rich Ed was our last possibility here. But I think I already have them on a team right there. Rich and Ed are a team. Rich and Ed are a team. So we already got that team going. So in this case, if we don't regard ordering as we do with a team, there's only 3 possible teams. So when we arrange objects and don't regard the ordering, so the order doesn't create something new when we change the order, these are called combinations. So combinations, in this case, there are 3 of them. So there are 3 different arrangements of these students where we're picking 2 of them out of the 3 to be on a team together. So 3 combinations of students. So 3 combinations of 3 students taken 2 at a time. All right, so I'll give you some keywords to kind of help you figure out the difference in the problems, but I'm going to just put up here with permutations, anything that talks about positioning, like first place, second place, rankings. Again, thinking first place, second place, positioning, ranking objects, people, or whatever it is that you are working with is going to result in permutations because different orders are different. First place is different than being in second place. Combinations, on the other hand, if you're talking about a team of people, so everybody on that team is equal, or you can kind of think of it as just collections of objects. So a collections of objects. So you're not positioning them, you're just thinking of them as one group together. So team or collections of objects are some good words to remember. All right, so the idea then is, how could I know that this answer was 6 ways and this answer was 3 ways without having to always list all of these possibilities? And we're going to rely on technology to help with that. So first, I just want to kind of repeat this with the examples we're doing. So there's 6 ways to award scholarships. So to award the scholarships, I'm just going to say award the money because it's shorter. 6 ways to award the money. And then down here, we're saying that there are 3 teams possible. So there's 3 different teams possible. So how could we get those answers without needing to make a list? So what we're going to do here is look at our calculator notation. So I'm going to write a P here, a capital P for permutation, and underneath I'm going to write C, capital C for combinations. So we're going to count how many ways there are to arrange 3 people. So I'm going to have a subscript 3 on the left side of the P. So this is our, you can think of it just the total number of objects, people, or whatever they happen to be. So this is your total. And I'm just going to switch to red here so this stands out a little bit. So this is the total. And our calculator, we'll call that N. So N is 3 in this case. We've got 3 people. And then the subscript on the right side, the 2, is going to indicate how many of those people we're choosing to put in one of these, in this case, 2 positions, first place, second place, $1,000, 500. So the 2 here is the number of them that we are actually selecting. And sorry, my computer's just freezing on me for a moment. There we go. So this number is the number of objects being selected. So in this case, people, 2 people being selected. And our calculator will use lowercase r for that. So our r will be 2. All right, so let me show you how to do this on the calculator. So 3p2, permutation of 3 people taken 2 at a time. All right, so you're going to type the 3 first. So there's our 3. And then to get to permutations, you're going to hit your math button and then go over to probability, choice 2, NPR. So NPR, enter to get that on your home screen. And then type in the 2 and enter. And that's how you will get an answer of 6 without having to go through this list. So that value, I'm just going to write it up here at the top. So P, 3P2 is our calculator's way of helping us out and giving us the answer 6. Okay, let's try it with the combination. And it's basically same idea, but now with the team here, 3 people, we're picking 2 people to be on a team. So this is the N, this is the R, and then we're going to get that answer using our calculator. So we know that there are 3 ways to do it, and the calculator should confirm that for us. So again, you hit the 3 first, so 3, and then your math button, go to probability, and choose choice 3 now, NCR, and enter. We still have to hit the 2. So there is our 3C2 combination, enter, and that's where that 3 can be found using technology. Okay, so a couple notes here. The subscript on the left has to be the bigger of the 2 numbers. They could actually be equal, but this number on the left N cannot be smaller than the one on the right, because the one on the left, the N, always represents the total. In this case, it was the total number of people, but the total number of objects possible. The one on the right is how many of them you're selecting. So I want to go back to a problem that we did with the fundamental counting principle when we looked at the number of different ways we could run errands if we have to go to 6 different stores in one day. So this actually is an example of a permutation of objects because positioning would matter to us. So I think I used the example of, for my 6 stores, let's say I need to go to Trader Joe's and I also need to go to Target. So I could go to Trader Joe's first and Target second, or I could go to Target first and Trader Joe's second. Those would be 2 different plans for running my errands that day. So in this case, positioning would matter to us. Where are we going to go first? Where are we going to go second? So another way to get this answer that we found before 720 would be to say, let's put it up here. So permutation, because different orders are different routes for the day as we travel to the stores. We would have 6 stores that we'll be going to, and we're choosing all 6 to visit. So those 2 values can be the same. So for these 6 stores, how many ways can I arrange 6 of them in the order I would like to visit? And again, typing that on the calculator, you would do the 6, your math button, you go to your probability menu, and you pick your NPR. And then you enter the subscript on the right, and that would also give you 720. So permutations are actually something that could be done using the fundamental counting principle we did before. So we kind of have a choice there. But when it comes to combinations, we will rely here on technology. And let me just show you then my summary at the bottom: permutations versus combinations. And I talked about some of these words to think about. So we're arranging things and there's positioning to them, like first place, second place, or collections, combinations, where we're simply looking at like a team of people or just a group where we're not thinking about ranking or positioning them. We are going to use technology, RTI 83 or 84, like we showed there. I did in the notes just put some of these, the two formulas for permutations and combinations. So we could do these formulas by hand, but we will take advantage of technology. And you're welcome to check out the formulas if you would like. But we'll go the technology route and focus our time on reading questions and figuring out if it's a combination question, a permutation question, or if it's a question that will be done using, this was the fundamental counting principle. And I'm just going to write that here. So this was the first technique we saw as we started counting rules. This one is called the fundamental counting principle. And that's where we multiplied each decision we made by the number of choices we had for each of those decisions. All right, and so what we'll do next is look at some examples.